We have a viewer submitted problem today, and it says, here is a simple task. Given 2 piles of rocks, you have 3 turns. Take 1 stone from pile 1, take 1 stone from pile 2, take 1 stone from pile 1, and take 1 stone from pile 2. 2 players take turns making moves. Whoever can't make a move because of lack of stones is considered the loser. The question is, can you guarantee to win starting from configuration 12,345 in the first pile, 23,456 in the second pile? And then we're given other considerations. Can we win from 23,456 in both piles? Okay, there's a class of games that look like this, and I'm not positive, but typically from what I've seen, most games like this, they basically have a set of winning positions for either the first or second player. The first thing about this specific game that comes to mind is that it doesn't matter whether they're, it doesn't matter how many are in pile 1 or pile 2. Like, it's symmetric between pile 1 and pile 2. If pile 1 is X and pile 2 is Y, and if that's a winning position, then if you interchange X and Y, that would also be a winning position. Another thing about these types of games is that to try and figure out what the winning positions are, it often helps to kind of work backwards. So basically, whoever takes the last stone is the winner, because it says that whoever can't make a move because of a lack of stones is considered a loser. So if you take the last stone, you're a winner. So the following 3 conditions are a winning state for whichever player plays. So these are winning states. Let's go back. Let's go back. So this in particular means that, 2-0 and 0-2 are both losing states. So these are winning states. If you're looking at the board and that's what the state is, it means you're about to win. If you're looking at the board and you see this, you're going to lose. And I suppose then also we can add 2-1 and 1-2. If it's 2-1, oh wait, no, these are not losing states. These are in fact winning states. Because 2-1, I can take a stone from the second pile and I hand it to you, and I hand you a losing state. So 2-1 is a winning state, as is 1-2 is a winning state. I wonder if whether a state is winning or losing depends on the difference between X and Y. Let's think about, okay, we have not covered 2-2 yet. 2-2 is a losing state because we can only go to 2-1, 1-2, or 1-1. And we've just said that these are all winning states. So this is a losing state. So another thought I have here is maybe if we just like expand from any given state x, y, x, y has to come from x plus 1y, x, y plus 1, or x plus 1, y plus 1. Now, if xy is a losing state, if this is a losing state, then these three are all winning states, because if I'm in this state of the game, I can take a move from the first pile. I can take a stone from the first pile to hand you a losing state. But we can't say the same necessarily if xy is a winning state. That does not mean that these three are losing states, because we could take an alternative move that doesn't take us to xy. Okay. So like I wonder if there's some kind of iterative way of here's what I'm going to try. So what I'm going to try here is I'm going to imagine I have each point on the grid corresponding to a state of the game, x and y, and this color will be a winning state. This color will be a losing state. So if we're at 0, 0, we've lost the game. And so that means these are all winning states. Along the axes, we just alternate. It should be kind of obvious, because if the number of stones in one of the piles is 0, then the only thing we can do is take a stone from the pile that does have something remaining. So once, for example, if y is equal to 0, meaning that we're somewhere down here, the only thing we can end up doing is moving to the left. Okay. Now, if we have a losing state somewhere, then all three nodes around it are winning states, because this is a losing state, meaning that if I'm in one of these three nodes, I can take a move which moves me here, and then I hand that state to the other player, and they lose. Okay, so there's a lot of winning states here. All right, and now this has to be a losing state, because from here I can only go down, left, or diagonal, and that hands a winning state to the other player, and so they will instantly hand back a losing state. And so then these are winning states. Again, this will be a losing state, and that a losing state. So I'm starting to see a bit of a pattern emerge here. I suppose a full proof of the classification of which states are winning and losing would be based on maybe some kind of induction or something like that. I'm not going to work through a full proof, but it's pretty clear that the losing states, this point here is 0, 0. So a state is losing if both of its coordinates are even. This state here, for example, is 1, 2, 3, 4, 5, 6, comma 2. So we can say x, y is a losing state if and only if x and y are both even. So in the original message I got asking, can you guarantee a win from particular configurations? The first configuration was 1, 2, 3, 4, 5, comma 2, 3, 4, 5, 6. So this is a winning state. And then it asked about the configuration 2, 3, 4, 5, 6, 2, 3, 4, 5, 6. And this is a losing state. So if you start the game, if you're the first player and you start the game in this configuration, you cannot guarantee yourself a win. In fact, the other player can guarantee that you lose. And if you start the game as first player in this configuration, you can guarantee yourself a win by taking moves appropriately. And in fact, the strategy is, from any given state you're in, just make sure you transition into a state where both coordinates are even. So no matter which point you choose here, you can always find a legal move which takes you to another point where both coordinates are even. And as long as you always do that, you'll win the game. Yeah, this is a cool problem. Again, there's like a whole class of games similar to this. But I'm going to be honest, this is the first time I've actually worked out a classification of winning and losing positions and what the winning strategy is. Yeah, thanks for the submission here. If I have more to say, I'll put it down in the description. Thanks for watching.